Hello everyone, I'm Rachit Nigam, and I'll be giving a talk on our paper, A Compiler Infrastructure for Accelerator Generators. This work was done in collaboration with my co-authors Samuel Thomas, Jijing Li, and Adrian Samson. So I have a confession to make. Before I was into hardware design, I used to be a software programmer. And the one really great thing of the software ecosystem is that I always had the right set of abstractions for the job I was doing. But the hardware ecosystem is a bit different. Even though we have a bunch of different languages, all of them operate at the same level of abstractions, specifically those of gates, wires, and clock cycles. There have been a bunch of new programming models proposed that try to raise the level of abstraction, sometimes all the way up to software languages. But a key challenge with these new languages is that they must target hardware design languages if they ever want to run on an FPGA or have a chip fabricated. And for each new language, we have to come up with a compiler that not only supports its abstractions, but also does a bunch of tedious work like optimizing resource usage, generating FSMs, and breaking up critical paths. For every compiler we build, we redo this job. And this is really a lot of wasted work. So what we're trying to do is build a shared infrastructure called Calyx that can do all of these optimizations and analyses once, do them right, and have new programming models directly target Calyx instead of hardware design languages, and reap the benefits of a shared ecosystem. If this sounds familiar, this is exactly what languages like LLVM do. LLVM, which is a software intermediate language, captures the control flow of programs really well, but it fails to capture the structure and timing behavior of these programs, which is really important when building hardware designs. Fertile, on the other hand, can capture structure and timing behavior of hardware designs really well, but fails to capture the control flow. And this is because in hardware designs, control flow is often encoded using structural elements like registers and adder, which are completely indistinguishable from data flow elements. The key insight of our work is to come up with a unified representation that can capture both the control flow facts and the structural and timing behavior of the hardware design. I'm going to quickly give you an overview of what Calyx programs look like. Calyx uses a control sublanguage that has operators like if, while, and par that capture its control flow behavior. It also instantiates hardware data flow graphs explicitly and gives subgraphs certain names for when they do some semantically meaningful action. For example, the if node can say this subgraph is used to compute my conditional. And each control operator can refer to same or distinct parts of the hardware subgraph to do its computation. In order to instantiate the hardware graph, we first create hardware modules, give them names, and give them bit widths. This goes in the cell section of a Calyx program, while the control flow is encoded in the control section. Finally, the connections between these hardware instances are defined in the wire section, and we use the group abstraction to give certain connections a name. It is precisely these names that are referred to by the control program. For example, the while loop can say, execute the connections in the group green to perform the computation in my body. Now, this control flow and structural distinction is really useful for optimizations that need to rely on both of these facts. I'm going to quickly give you an overview of one such optimization. So here's a program that executes a conditional that executes two different hardware subgraphs, both of which use distinct adders. Now, from what we know about conditionals, we know only one of these branches will ever be taken, which means we can show that these two adders never run in parallel. And it is this combination of the control flow fact that these two branches never run in parallel and the structural fact that these two adders are distinct that allows us to implement an optimization that shares these two adders and reduces the resource usage of our hardware design. Calyx makes these kinds of control flow based optimizations easy to do for hardware accelerators. It also makes it easy to transfer programs to implement these optimizations. In summary, our paper on Calyx demonstrates its flexibility by building two front-end compilers, one for a loop-based imperative language for accelerator design, another for a systolic array generator. We implement Calyx in a modular pass-based compiler infrastructure and implement several control flow optimizations. And finally, we show that Calyx can generate synthesizable hardware designs and compare them to the state of the art. For more information, please check out this link, and thank you for your time.